Welcome. So let us have a quick look at moments of inertia. This is engineering mechanics, and I want to discuss moments of inertia briefly. So what do we mean by moment of inertia? Moment of inertia. So this has to do with moment of area. And indeed, when we discussed centroid of areas, we talked about the first moment of area, which was for an area in the xy plane. This is our x-axis, and this is our y-axis. So let's say we have this area right here, okay, and we want to get the moment of this area, for instance, about the y-axis. Then we will draw this distance. I mean, this will take note of this distance from the centroid of the area, okay, to the x-axis and to the y-axis, and we call that distance x bar. Why is it called x bar? Because it is a distance along the x-axis, and if we're going to do that for the y-axis, it's better to just extend this out. We see that the distance here is going to be our y bar, okay, and it is such that if we want to get the moment of this about this point, we say that our x bar is going to be given by, or say the moment of this, say q x, the first moment of area about the x-axis, that is going to be this area, whatever this area happens to be, multiplied by this value here, which is its distance, distance from the center, okay, distance from the axis of interest, perpendicular distance, of course, from the axis of interest to its center, to the center of that area. So in this case, um, moment about the x-axis will be this area multiplied by the perpendicular distance from the axis. So that is going to be y bar multiplying a. And if we want to get the first moment of area about the y-axis in the same vein, that will be the center of the area located, then what is its perpendicular distance from the y-axis? That is x bar, which is called the centroid. Okay, the parameter that gives us the centroid of this area. So that's basically just going to be x bar multiplied by a. And of course, this is for an area that we know clearly what its value is, what the actual area is. So we will usually or typically deal with differential area. So if we don't know what the total area is, we can pick a differential area on this, then integrate over the differential area. So if we are going to do that using the differential area, we know that area itself will be given by, so if we have a differential area, let's illustrate that separately. So this is basically what this actually means. If we have a differential area, so let's say that we'll pick something like this. We have this area. So we can't tell precisely what its centroid is. So we don't know what its centroid is, but we now decide to pick an elemental area of this. So this is the elemental area. It is denoted as dA. And then for this elemental area, we decide to find out what the centroid of the elemental area is. So we say that I find out the centroid of this elemental area. We will have its x coordinate or y coordinate to be given by this distance. So we can call it y elemental area bar. And if we get the distance, okay, along the x-axis, we can call this x elemental area bar. And that will give us, so this is still our y-axis and this is our x-axis. So if we want to calculate the centroid for this area, what we simply do is we get everything we need to get for the elemental area. Then we know that by the time we integrate the expression for the elemental area over the entire area, that is whatever parameters we have there, we will find out how it varies over the entire area, then integrate along that line. Then we're going to have it for the entire area at the end of the day. So it just follows that when we get this for the elemental area, it means that if you want to get qx, okay, for the elemental area, it is going to be equal to x, that's y elemental area, that is moment, first moment about the x-axis, that will be y elemental bar multiplied by the A. And if we want to get it for the total area now, and we want to get QS for the total area, we'll now say this is integral of y elemental bar dA. If we want to get similarly for the moments about the y-axis, we will say that our QY for the elemental area would be equal to x elemental dA. And if we're going to get it for the entire area, our QY will be integral of y elemental, okay, dA. Okay, so sorry, this is x elemental, please. So this is x elemental dA. And using this idea, we can also get from the elemental area expression, we can get the total area for this of the elemental area. So we're taking all of these integrals over the entire area. This is taking over the entire area. So this is taking over the entire area. So the integral of this will give us the total area. So if we come back to this equation, we said that the moment of the area, the first moment of the area about the x-axis is given by y bar a. We have also seen that the first moment of the area is also given by this integral. So if we equate these two, so let's say this is equation A and this is equation B, and then we come here and call this equation. So we have this equation here. Let's say this is equation C and this is equation D. So from that, we can see that we can now get the centroid of the area by just relating these two. So from equating equations A and C. So you can see equation A has to do with QX, the first moment of area about the x-axis. Equation C also has to do with QX. So using equations A and C, we will obtain this relation. We will see that our y bar a, this y bar a right here. So we see that our y bar, okay, multiplied by a. So please let's write that on another line so it's clear. Our y bar multiplied by a is equal to, that is this expression here, is equal to the integral of y elemental bar with respect to a, and this will be integrated over the entire area. So again, we know that the area itself is just integral of the A. So we can just write this as y bar multiplying the integral of the A, of course, it will be taken over the entire area as well, is equal to integral of y elemental bar the A over the entire area. So from here, we see that if we want to get the y bar, which is the y coordinate of the centroid of that area, it is going to be given by, if we're able to get an elemental area, we'll just take the integral over the entire area of y elemental bar, which is the centroid of the elemental area, and this is the A divided by integral of the A over the same area. So this is the idea behind our discussion on centroid of area. So basically, we were taking moment of area, so to speak. You can put moment in quotes now, but it was first moment of area. I mean, similarly, by going through the same process, we'll see that our x bar for the entire area will be given by the integral over the entire area of x elemental bar the A, and that is going to be divided again by the integral over the entire area. So this gives us the entire area. So at every point here, we were taking the first moment of area, okay, the first moment of area about the respective axis. So we see that this is equal to this expression. So now, when we say moment of inertia, it is actually just literally second moment of area. Again, this expression here is first moment of area. Why are we calling it moment, or why can we regard it as moment? Now we discussed moment of forces. We said at the most basic level, basic level, we can define moment of a force as, you know, to a layman, force multiplied by perpendicular distance. We know it involves much more than that when it comes to vectors. Okay, But the same idea is carried over here. So when we get this area multiplied by its perpendicular distance from the x-axis, we can call it its first moment of about the x-axis. That's moment of this area about the x-axis. So y elemental bar the A is moment of that elemental area about the x-axis, because this is perpendicular distance from the x-axis. So we get x elemental, okay, bar multiplied by dA, that is moment of this elemental area about the y-axis. So that is the idea behind this process of getting the centroid of an area. But we are not here to discuss centroid anyway, so don't get carried away. So what is important is for you to recall what the first moment of area looked like, and now for us to get second moment of area, second moment of area, or what we call moment of inertia, simply means the moment of area, that is moment of the first moment of area. So why are we troubling ourselves with all of this? Actually, it just happens that when you're doing some analysis with structures, you will usually come across that term in most of the results having to do with structural analysis. So that is why we're just studying that particular term, and so that we can have a definite way of actually calculating it when we have to analyze a structure. So we wouldn't have to calculate it separately for each structure we want to analyze. So it's good that we study moments of inertia, know how it relates with different axes and all of that, so that by the time we need to make use of it, by the time we come across it in our analysis, we can easily identify it and we already know how to handle it. Okay, so that's what we're doing here. So basically for an area now, so let's get to business. For a given area, so we have an arbitrary area. So this is area A, and you want to get the moment of this area about, say, the x-axis. So if it is moment of inertia now, which is second moment of area, we know that normally moment of area will be whatever you have here, okay, multiplying this distance multiplying the area will give you the moment about the x-axis. But here we're interested in moment of inertia, the second moment of area. So about the x-axis, it will be, so because it's the second moment, that means what we have gotten before, which normally should be the area multiplied by this perpendicular distance, which is y. We are now multiplying it again by the perpendicular distance, which is still y. So at the end of the day, this will be y squared. So it will just be y squared a. So what we are doing is that if we get it for an elemental area on this, as we always did, and we get y, that's the distance from the x-axis, then this will just be integral of y squared a over the entire area. Okay, that is just similar to how we did something like that here. Just that this one was for the elemental area, we had to put a bar there. So here we're using y directly. Okay, they actually just have the same implication in this case, but we'll see how we apply this when we solve some problems now. So this is the moment, the moment of inertia or second moment of area, okay, about the x-axis. Please take note of the fact that when this is about the x-axis, this is y squared. Okay, and similarly, when it is about the y-axis, if we're going to have iy here, what we'll have there will be x squared dA. So it will be integral of x squared dA taking over the entire area. So we pick an elemental area there, we take this over the entire area, it will give us the moment of inertia about this y-axis. So that is the idea. This is the particular quantity that we will now trouble ourselves with in this lesson. So how do we deal with this? That means that just like we did for centroid, we'll begin to bother ourselves about what will this look like for different kinds of shapes, and we'll start off with very basic shapes and see what it's going to give us. Okay, so this is for moment about the x-axis, moment about the y-axis. So we also have what we call the polar moment of inertia. So this is the origin of the coordinate system. So imagine that there is an axis here that is perpendicular to this coordinate system. Let's say it is pointing out of the plane of this book. So you can imagine that there is a z-axis which is perpendicular to this plane and pointing outward. We might also want to get the second moment of this area about that axis. And if we're going to do that, the perpendicular distance from this area to that particular axis will be this line. Okay, and this is usually called R to tell us the position of this area relative to the origin. Okay, because the that axis, z axis is perpendicular to this plane. Of course, this is just the perpendicular distance from the area to the axis of interest. So we call that the polar moment of inertia. So when you hear the word polar moment of inertia, it is polar moment of inertia. So it will just be given by the integral of r squared, because the perpendicular distance in this case is r squared. And that will be integral of r squared dA taking over the entire area. That will give us the polar moment of inertia. And of course, knowing that x bar or x and y are perpendicular distances, we can tell that this one is x and this one is y. So definitely r squared by Pythagoras theorem, if you extend this here, you see this is going to be perpendicular to this. So this distance is y, this distance is x. So basically r is going to be equal to, so from here we know that r by Pythagoras theorem will be equal to the square root of x squared plus y squared. I'll say r squared will be equal to x squared plus y squared. So that means that our polar moment of inertia can be simplified further. If we simplify this further, we get we get this to be equal to the integral of r squared. Instead of r squared, we know this is the same as x squared plus y squared dA, and taking over the entire area. And when we split this out, this will be integral of x squared dA over the entire area plus integral of y squared dA over the entire area. So this is obviously Iy plus Ix. So because of that, we conclude that if we want to get the polar moment of inertia, it's sufficient if we get the moment of inertia about two perpendicular axes that passes through that point, and then we add them up. Once we add them up, then we know we have obtained the polar moment of inertia for the particular point. So that means if I want to get the polar moment of inertia about point O, it's sufficient to get polar moment of inertia about this x-axis and this y-axis, that is two perpendicular axes that intersect at the point of interest. Once I have that, I add them up. That will give me the polar moment of inertia about the point of interest. So for this case, we say that our polar moment of inertia J naught is obviously just equal to Ix plus Iy, or Iy plus Ix if you like. So that is our polar moment of inertia. This is called the polar moment of inertia. So all of these are area moments of inertia. In another lesson, we'll talk about mass moment of inertia. So you can have mass moment of inertia. I mean, the same idea, just that instead of the A, we'll be having the M there. So all the other variables, I mean, and parameters remain the same. So that's what we want to do now. Now for, I mean, we want to deal with moments of inertia of area now. So let's focus on that first. So this is polar moment of inertia. This is how you get it. This is moment of inertia about the x-axis, moment of inertia about the y-axis. So if you have to get moment of inertia about an arbitrary axis, you follow the same process. Get a perpendicular distance of the area from that axis of interest, and then take the integral of the square of the perpendicular axis, okay, multiplied by the a. So I mean the perpendicular distance multiplied by the a. So it's as simple as that. We also usually or typically talk about what we call radius of gyration. So you come across the term radius of gyration. So the meaning of this is that for each of these, for instance, we know that we can have Ix. We have Ix from what we've discussed now. We have Iy, moments of inertia about the y-axis, and we have J naught, polar moment of inertia. So if we are able to, can we get a number or a value which is a length parameter, such that when we take its square and just use it to multiply the area of interest, it is going to give us this moment of inertia directly. I mean, instead of going through all of these processes. So, that is similar to what we did here. Here, we found centroid of the area. It is such that when we knew the centroid of the area, to get the first moment of area, it was very straightforward. We just multiplied the centroid by the first moment of area. I mean, sorry, we just multiplied the centroid by the area, and this gave us the moment of that area about the x-axis. Here we just multiply the centroid, as the x component of the centroid, by the area. It gave us the moment of area, the first moment of area about the x-axis. So now we now ask ourselves this, that okay, we know that moment of inertia is given by, for about the x-axis, is given by integral of y squared dA. But can we find a particular value such that by the time we square it and just multiply it by the total area, it gives us this whole thing without us having to do any integration any further? So that is what we call the radius of gyration. So if I want to get radius of gyration about the x-axis, so radius of gyration is generally denoted as k. So if we do case of x, it corresponds to the x-axis. We can have case of y, which corresponds to the radius of gyration about the x-axis. We can have k naught, which corresponds to the polar radius of gyration. But the idea with all of them remains the same, that if I have kx and square it and multiply by the area, it will give me this moment of inertia directly. And the same thing apply here. If I have ky, I square it and multiply it by the area, it will give me this moment of inertia about the y-axis directly. If I have k naught and squared it and multiply by this, it will give me the polar moment of inertia directly. So this is the idea with radius of gyration. So you can think of radius of gyration as what you would of the what do you call now, the coordinate of the centroid of area when we talked about the first moment of area. Okay, so that is the idea here. And if we were going to proceed with this and make kx the subject, that means kx will be equal to ix, so the square root of ix over a. If we make this the subject, ky will be equal to the square root of iy over a. And if we make this the subject, we'll have k naught is equal to the square root of j naught over a. So that is the idea. So if we're asked to find the radius of gyration, this is the way to go. This is how to go about it. Okay. So I think we've discussed the fundamental things now. So let's look at how to get the moment of inertia of an area from the first principle, that is by carrying out this integration directly. So let's have a look at that with some example. And of course, we're going to start off with a very basic example. So let's say that we have a rectangle. So now we want to determine the moment of inertia of inertia of a rectangle about perpendicular axis at its base. All right, so this is what we mean by that. If we have a rectangle, so this is a very good building block for studying moments of inertia. So if you have x-axis and y-axis, and then we have this area. It's a rectangular area now. So let's draw something that looks better. So this is a rectangular area. We have this rectangular area, and now we want to find out, this is the area, we want to find out its moment of inertia about this x and y axis. So this is at its base, this is at its base. Okay, this is perpendicular to its base. Okay, so now normally if we have a rectangle, we'll have the dimensions of the rectangle. So you can say that the base of this rectangle is denoted as b, and then we denote its height by, say, d. Okay, so we call the height d. So we have something like this. This is the height, we call it d. So we want to obtain the moment of inertia of this area from the first principle, that is by direct integration. That's what we mean by that. So this is a rectangular area. We want to get the moment of inertia, and the way to go about that using direct integration is to form or extract an elemental area. That is, we extract an elemental area, which is usually or typically a what do you call it now? A rectangular strip. So this is what we mean by that. So let's redraw this. So let's say we just want to solve the problem now, and we have this diagram reproduced here. This is our x-axis, this is our y-axis, this is the rectangular area that we have to deal with. So for us to get moment of inertia about the y-axis, we will use a rectangular strip that is parallel to the y-axis. So we can take this as that rectangular strip. This is a very small area, and if that is the case, we'll say that this width of this rectangular strip is given by the x. Why do we call it the x? Because it is a small width that is along the x-axis. Okay, so we call that the x. So this is called the x. And of course, this height, the height of this elemental strip is still the same thing as the height of the whole rectangle, because this cuts through the whole rectangle. All right, so we still have the base to be given by b and the height here to be given by d, which is this distance from this point to this point. Okay, and this is still the distance from this point to this point. So we're good to go. So how do we now get the moment of inertia? So what we do is define our dA. This is the elemental area. This rectangular strip that we have defined now is our elemental area. So that means this is our dA. So we now ask ourselves that what is the area of this rectangular strip that we have now defined? We know the area of a rectangle is given by length times breadth. So the length of this obviously is dx. So this length here, which is dx, we have denoted as dx because this is just a small length, a very small length, but it's along the x-axis. So this is dx, and the height of it, that's this length from this point to this point, is d, which is just the height of the area itself. So dA, which is the elemental area, is going to be given by d, this d right here, multiplied by dx. So this is d multiplying dx. Please don't mix them up. This is dx. This dx is representing this width. D is representing this height. Okay, I think we should change that to avoid confusion. Let's change this to h instead. It doesn't change anything. That's just a change of what do you call it? A change of symbol or variable, if you like. So this is going to be by that h multiplying dx. So this is the elemental strip. Its height is h and its width is dx. So by that, we can integrate over this to obtain our iy. So we want to get the moment of inertia about the y-axis. So if we want to get that, we know that our y is just going to be the distance of this area, of course, perpendicular distance of this area from this axis. And of course, that will be given by the x coordinates of whatever point that is. Okay, and we know that moment of inertia about the y-axis from our definition is given by integral of x squared dA from over the entire area. So that's what we have right here in our definition. Moment of inertia about the y-axis is given by integral of x squared dA. So we can do that right here. Let's evaluate the integral of x squared dA right here. So our x is still x here, and that is the advantage of just using a an elemental strip or a rectangular strip that is parallel to the axis about which our moment is required. So we want to get moment of inertia about the y-axis, then we should use, or it is best we use a rectangular strip that is parallel to the y-axis. Of course, we can still use something that is perpendicular, maybe something that is parallel to the other axis. Yes, we'll talk about how to do that, but we're starting off with this. We're using this expression. We're using this elemental area or this rectangular area. So how do we define this now? How do we evaluate this? So we'll go ahead to say that the moment of inertia of this about the y-axis is equal to integral of x squared, still x squared, dA, our dA, we have seen it here to be h dx. So we'll put that h dx there. So by this substitution, we have seen that this integral, because of the x that we have here, it means this integral has to be done with respect to x. So if it has to be done with respect to x, then when we want to get this over the entire area, what we ask ourselves is, how does x vary over the entire area? So whatever we have here at the end of the substitution and simplification tells us how this integral will be evaluated. It has to be a definite integral. So what will be the lower limits, what will be the upper limits? And to do that, we look on the x-axis, see how the entire area varies on the x-axis. We ask ourselves what is the minimum value of the x coordinate of this on this area, okay, and what is the maximum value of x coordinate on this area. So the minimum is this point. You can see at this point our x coordinates will be 0, and we see that from this point to this point the distance is b. So that means on this area x will go from 0 at this point to b at this point. That will be the end of the area as far as the x-axis is concerned. That is, we take the extremities of the coordinates, x coordinates on that area. Okay, that's what we're interested in, because this one is the x. If we had used an elemental area that carried the y, we would ask ourselves how does y vary over the entire area. We'll pick the lowest value of y coordinate there, that will be our lower value here, and the highest value of our y coordinate, that will be our higher value here. So in this case, it's obvious that this goes from 0 to b. So we can now simplify that. We say h is a constant. That's just the height of the rectangle. So we can move it out of this integral sign. Then we're going to have left x squared dx, okay, from 0 to b. So how do we integrate this? X squared with respect to x. That's quite straightforward to get from our knowledge of calculus. This is going to be h into x to the power 3. That's x raised to the power 2 plus 1 over 2 plus 1. That's 3. And then we will evaluate these between 0 and b. That is, we substitute x equal to b here, and we substitute x equal to 0. Then we subtract the differences. So basically, this is going to give us h into, when we substitute b here, that will be b to the power 3 over 3. Then minus, when we substitute 0, that is 0 to the power 3 over 3, okay, which is 0. So then at the end of the day, we will see that our moment of inertia about the y-axis is hb cube over 3. So that's how we can get moment of inertia by direct integration. So it is quite clear and straightforward to deal with that way. So this moment of inertia of the rectangle, which we have just done now, is very important. It is fundamental to the analysis of moment of inertia for other areas. So please, you need to know this offhand. You need to know what it is for moment of inertia about a base. When we take it about this base, we can see that it's hb cube over 3. When we take it about the base, the base here, this is y-axis, which is at the end of the rectangle. So it is going to be hb cube over 3. H is the height or the length dimension along that particular axis. Okay, b is the length dimension along the other axis. So it is the length dimension along the other axis that is being raised to the power of 3. So as expected, if we evaluate this about the x-axis, we should obtain 1 over 3, just like we had 1 over 3 here, of bh cube, because in that case, along the x-axis, the length dimension will be b, along the perpendicular axis, the length dimension will be h. But let us check that for ourselves. The reason we are doing this again is because it is fundamental to others that we are going to solve. So it is important that we know this, because when solving, generally we'll make use of rectangular strip. So it is good if we already know what the moment of inertia of a given strip is, so that we won't have to do a strip in the vertical direction, a strip in the horizontal direction anytime we have to get moment of inertia about x-axis and about y-axis. So we won't have to do that once we already know what the general formula is for a rectangle, which we will then use for a rectangular strip. We'll come across a rectangular strip. So let's see how this works now. So if we were interested in Ix, that's the moment of inertia about the x-axis, it is ideal, yes, to have the rectangular strip chosen parallel to the x-axis. So we can use this rectangular strip that is parallel to the x-axis. So if we are using this, That means for this case, our elemental length will be, I mean, the width of this will be an elemental length along the y-axis. So we can call this the y. And of course, the length of this still is b. The length of this is still h. So if we are going to do this, that means in this case, our dA, which is the area of the rectangular strip we have so chosen, is going to be the length of this, which is b, multiplied by the width or the height, if you like, which is the y. So our dA here will be b dy. And how would we get the moment of inertia about the y-axis? We'll find out what the perpendicular distance from the area to the x-axis is, about the x-axis now. So that is our y. It will be the y coordinate of whatever point this area is located. Okay, so that is that about that. That means then, if we want to get from this moment of inertia about the x-axis, it will be the integral again of y squared dA. We already see clearly that this is our y here, and so by that, this will be equal to the integral, of course, taking over the entire area. This will be integral of y squared dA. What our dA again? Our dA is b dy. So this is the a here, it is b dy. And now we have to integrate with respect to y. So dy means it has to be done with respect to y, or along the y-axis. And how do we then define this over the entire area? We ask ourselves a question similar to what we did in the first case. How does y vary over the entire area? Over the entire area, look at it, y at this point is 0, y coordinate at this point is 0, y coordinate at this point will be h, because the distance from this point to this point is h. So that means over the entire area, y goes from its value here, the lowest here, which is 0, to the highest here, which is h. So integrating over the entire area in this context now means integrating from 0 to h. So what is the implication of that on our integral? This will mean we have b is a constant, that's a length dimension for the given rectangle, so we can move it out of the integral sign. This will be b integral of y squared dy from 0 to h, and this is going to give us b integral of y squared with respect to y. That is again y to power 2 plus 1, which is y over y to power 3 divided by 2 plus 1. And of course, we will evaluate this from 0 to h. And so when we substitute h here, we're going to have b into y to power 3. We're substituting b for, I mean h for y now, that's h to power 3 over 3, minus, when we substitute 0, that is 0 to power 3 over 3. So with this, we now have our moment of inertia for this rectangle about the x-axis to be equal to bh cubed over 3 as expected. So we can see that this is bh cubed over 3 because it is taken with respect to the x-axis. So I said you should know this offhand, you should know this by heart. That's what I mean by that. You should know this off head. Okay, so anyhow you understand the language, you should know this offhand. It's important. So that you don't mix it up. Was why I told you earlier that the moment of inertia about an axis at the base is simply going to be the length dimension at that base that is along the particular axis multiplied by the cube of the one on the other axis, which is h in this case. So the one on this axis, which is our x-axis here, is b. Okay, we're not taking the cube of that, we're taking the cube of the one on the other axis, which is this, divided by 3. So you can see that's why we add this to be hb cube over 3. H it was the one along the y-axis that we took, and b was the one on the other end. So this is the form of the moment of inertia about an axis at the base of the rectangle. Why am I stressing that? Because if we took an axis that is through the centroid of the rectangle, we're going to do that shortly now. If we took an axis that is through the centroid of the rectangle, we will get a different result. That means the position of the axis on the particular area is very important. Obviously, that is important because we have said y squared will be measured from the elemental area. I mean, if we're taking integral of y squared dA, this y will be measured perpendicular to the x-axis and to be distance from the elemental area to the x-axis, like we've added here. So if our axis was located at this middle, we know that that distance will be different. So definitely we will get a different moment of inertia if we took an axis that is through the centroid of this area. So let us see what this gives us now. If we took an axis that is through the centroid of the area. So we're going to do that shortly for only one of the axes so that we can generalize the result and see how it works. So if the moment of inertia is going to be taking about axis through the centroid of the area, we usually denote it by bar. We usually put a bar on the whatever axis we're using. So if we have a rectangle, still we have a rectangle now to deal with. This is the rectangle, and this is the centroid of the rectangle. So these are axes that pass through the centroid of the rectangle. So we can call this one x bar, and we call this y bar. So when you see it like that, it means that usually it's used for axes that pass through the centroid of the area. Okay, so that means if we want to get the moment of inertia about x here, we call it ix bar. We want to get moment of inertia about y-axis here, we call it iy by bar. The process is essentially the same, just bearing in mind all of the concepts we've discussed. The process is essentially the same, just that in this case, we have firstly located the centroid of the area. So the axis is not at the base in this case. You know, in the previous two examples, the axes were at the base. So this was here and this was here. But now the axes are through the centroid of the area. So this is the centroid of this rectangle. We know that the centroid of the rectangle, that's just the center of the area. So this is quite easy to visualize. Again, the length along this axis will still be b in this case, and we're still taking it as b. So this length along this axis is still b, and the length along this axis is still h. So we're taking this as h still. So we have this length from this point to this point is h. And of course, if this is the centroid of the area, it means then that the length from this point to this point is half of the height, which is h over 2. And similarly, the length from this point to this point is half of the area, which will be b over 2. So that is that to for us to understand the location of the x bar and y bar. So let us go ahead and see what the moment of inertia will be now when we take this through x bar and y bar as we have just said. Let's have a new page here first. So we're not going to use this diagram any longer because of the different labels we've put. So let's just withdraw that. We're going to do it for just one of them. So let's say we're doing it for the y-axis, and then we compare the results and see what a similar result will be for the x-axis. So we have the rectangle reproduced here. We still have our length as before. This is b and this one is h. So for us to get the moment of inertia about the y-axis, again, let's use a rectangular strip that is parallel to the y-axis. So it will be through the entire area, now parallel to the y-axis again. And by that, it means again that the length here, this small length, will be the x again because it is an elemental length along the x-axis. And our elemental area, the a, will be area of this small rectangular strip. The width, the x, multiplied by the height, which is denoted as h, as we have said here, and we've used so far. So this is still going to be area of this is going to be h multiplying the x. So what's the next thing we do again? The distance of this from the x bar axis. Now this is y bar, this is x bar. So the distance from the y bar axis is still y in this case. That's the distance from this axis. So we still call it y. And so sorry, that is x, please, not y. That's distance along the x-axis, parallel to the x-axis, perpendicular to the y-axis. So we want to get our I y bar here to be again integral of x squared dA from, in this case, from over the entire area. So let's see how this works. This is going to be integral of x squared. What is our dA? Our dA is h dx. So we now ask ourselves, how does the x, so you can see this one now is the x. This is already implying that our integration has to be done with respect to the x-axis. So if we are doing it with respect to the x-axis, How does x vary on this area? So on this area, what is the minimum value of the x coordinate? What is the maximum value of the x coordinate? So that's what's important. So over this area, we see at this extreme, we can trace out the x coordinate, and at this extreme also we can trace out the x coordinate. So this is no longer from 0 to b like we had it before. So we know that this entire length is b, and half of it is b over 2. So definitely if we're interested in the coordinate of this point is going to be minus b over 2. Negative because it's in the negative side of the x-axis, or it is on the negative side of the x-axis. And the coordinate of this point is going to be b over 2, because we know the distance between these two is b. Okay, so if you don't get that, you can come back here to see. We said the width of this is b. That's given already as a parameter of the rectangle, and this is centroid of the area. So if it's centroid of the area, then this is half of the length of the base, which is b over 2. This is half of the length of the base, which is b over 2. So x coordinate will be to the left. We know that is negative. To the right is positive. So the distance from the origin to the left here is b over 2. So it will be minus b over 2, because we're interested in the coordinates. Plus b over 2 will mean it is this, the distance is b over 2 from the origin, but it will be to the right. To the left is negative, to the right is positive. Just like on the y bar axis, to the up or going up will be positive, going down will be negative. So that is the idea here. So that means that since this is now interpreted or implying integration with respect to x, then we must bear in mind that the integration has to proceed from the minimum value of minus b over 2 to the maximum value of b over 2, which is how x varies over the entire area, because this has to be integrated over the entire area. And the implication of that is like we are capturing all possible elemental lengths over this entire area, because this already defined perpendicular, it already captures everything along the y-axis. So you don't want to capture everything that is along the x-axis, and that's what this reveals for us. So we're good to go. Let us evaluate this integral. Like before, h is a constant, we can move it out. So this is h multiplied by integral of x squared dx from minus b over 2 to b over 2. So what will this give us now? This will give us y bar to be equal to h multiplying integral of this as before, that's x cubed over 3, that's x raised to power 2 plus 1 divided by 2 plus 1. Then we go from minus b over 2 to b over 2. And what does this give us? Again, we substitute when b over 2, when x is equal to b over 2, we're going to have b over 2 to power 3 divided by 3, minus when x is equal to minus b over 2, this will be b over 2, sorry, minus b over 2 to the power of 3 divided by 3. And we can now simplify this further to see what it gives us. This is going to be h into b to power 3, that's b to power 3, and 2 to power 3, that is 8, then divided by 3, that is 8 times 3, that's 24. So this is going to be b to power 3 over 24. So the same with this. This is minus to power 3, that's minus 1 still. So this becomes plus. And this will be b to power 3, that is b to power 3. 2 to power 3 is 8. 8 times 3 is also 24. So when we add up these two, this will be 2b3 over 24, which is 1b3 over 12. So what we have here will give us I y bar to be equal to hb cube all over 12. So this is the moment of inertia about the y-axis, that is through the centroid, that is the vertical axis that is through the centroid of the triangle. So we can now see that it is different from what we obtained before. What we obtained before was hb cube over 3 when the axis was at the base. We also obtained, when the axis was at the base, we obtained ix to be bh cube over 3, which is just like we are inverting or interchanging the positions of a and h and b. But in this case, it is quite different. It is hb cube over 12 for I y bar. And similarly, if we calculate, go through the same process, that is use a horizontal strip this time around and calculate for I x bar. So you can do that as an exercise. We will obtain something similar, just interchange. We have BH cube over 12. This is this moment of inertia through the center for an axis through the centroid of the area for a rectangle. Again, the same idea will still apply if we are going through a particular axis. The length across along that axis is b. That's the one that is not cubed, and the length across the other one is cubed. So once you follow the same process, just know this one is divided by 12 when it is through the centroid. When it is not through the centroid, it is divided by 3. So that's important. Please take note of that. Okay, so before we finalize this lesson, we will quickly talk about what we call the parallel axis theorem. So the parallel axis theorem is a fundamental principle when it comes to moments of inertia, and you will see the usefulness of this shortly. I said we have discussed here the moment of inertia of a rectangle because it is fundamental to our analysis of literally every other area, almost every other area that we may have to analyze for, that we may have to obtain their what do you call it now, centroid by direct integration, and even cases where we have to split into split a composite areas into simpler areas. We will typically come across rectangles. Okay, we commonly come across rectangles, so it is important to know, at least if you don't know anything at all, know the formula for the centroid of a rectangle. Know the difference between when the axis pass through the centroid of the area and when the axes are at the base of the area. So it is very important. So let's quickly talk about parallel axis theorem and end this lesson there. So parallel axis theorem has to do with how do we relate the moment of inertia about the centroid of the area and moment of inertia about any other axis parallel to one that passes through the centroid of the area. That is, if I know the moment of inertia about an axis through the centroid of the area, how can I relate it to, or how can I from it obtain the moment of inertia about some other axis that is not through the centroid of the area but parallel to the one I know, okay, that is through the centroid of the area. So that's the idea with parallel axis theorem. So we quickly state it now, and we will see that it actually works for the results we just obtained. Now we see that it actually works for it. Okay, so the idea is that if I want to get the moment of inertia through the centroid of the area, so if I have I x bar, this could be x bar or y bar through the centroid of the area, and add it to the area itself, that is the area of whatever shape I have, then I multiply by the square of the distance between the two axes. It will give me the moment of inertia about my arbitrary x-axis. So if I have an arbitrary axis, x, I want to get moment of inertia of the area about it, but I find out that x is parallel to some x bar axis, where this x bar axis is through the centroid of the area, and I know the area of the area or area of the shape, and then the distance between the x bar axis, that's perpendicular distance between the x bar axis and the x axis, then I can relate the two moments of inertia with this equation. So this is what we call the parallel axis theorem. Don't get carried away, please. This x bar here could have been y bar or z bar or anything. What is important is that this one on this right hand side is the one that passes through the centroid of the area, and this other one is parallel to the one here. They have to be parallel. That's what we're calling them parallel axis theorem. And this one carrying the bar, which is added to AD square, has to be through the centroid of the area. Once that is ascertained, then we can use this formula. So this is called the parallel axis theorem. So let's also illustrate that here. That means that if we have an arbitrary area, it means any kind of area now. So if we have an arbitrary area, we want to get this the moment of inertia of this area. So let's say this is the centroid of the area. We have an axis that passes through the centroid of the area, not exactly passing through it here. Let's make it better. Yeah. So this is our axis x bar. It passes through the centroid of the area, and I know the moment of inertia about this axis that passes through the centroid of the area. Now I want to get moment of inertia about some other axis. Now that axis does not have to be, it doesn't have to intersect with the area. It can be anywhere. anywhere it is, whether it is on the area or it is not on the area, it is away from the area. What is important that it is that it is parallel to this axis that is through the centroid of the area, and of course in the same plane in this case. So what I need is just the distance between this and this. That's what we are calling D in this case. So this is D. What I need again, if it were this axis, will be this distance between this and the axis that passes through the centroid. So we can call that D. So we can call this D1 and D2. So this, if this is axis x2 and this is axis x1, by parallel axis theorem, it means if I want to get the moment of inertia about this x1 axis, and I already know the moment of inertia about the x bar axis, and I see x1 axis is parallel to x bar axis, I don't need to calculate this from the ground up any longer. I can just get it by using this parallel axis theorem. So it will be the moment of inertia about an axis through the centroid plus the area of this shape multiplied by this perpendicular distance between the two axes, d1 in this case squared. And similarly, if I wanted to get ix2, moment of inertia about the x2 axis, since I have seen that this is parallel to an axis through the centroid of the area, that will give me, or will be given by the moment of inertia about an axis through the centroid of this area plus the area multiplied by the perpendicular distance between these two axes, d2 and then squared. So this is the provision of the parallel axis theorem. So to finalize this lesson, we will ask ourselves, does that apply to the areas we just discussed now, the rectangular area we just discussed now? Yes, it should. If it is correct, it should. So what is the area of the rectangle that we just discussed now? So let's write it out here. So for the rectangle, or for the rectangle, if you like, we can call it our rectangle. We know that the area of the rectangle is base times height, so we've seen that it is BH. No matter how you are looking at it, it's just the product of the dimensions. So it is going to be this times this, length times the breadth, or height times the breadth, or width times the breadth. Anyhow you see it, it's still just BH. So that is the area. Now, if we have, look at it, we've seen that the moment of inertia about an axis through the centroid of the rectangle. So this is the rectangle now, just anyhow. And this is our x bar, this is our y bar. We have seen what ix bar is. Okay, we have obtained ix bar. For this case, we said this dimension is b, this dimension is h. So we have obtained our ix bar to be equal to bh cube over 12. We have obtained our iy bar to be equal to hb cube over 12. So if we didn't know the moment of inertia about an axis at the base of this rectangle, okay, that is parallel to the x-axis, this x bar, and that is at the base of this rectangle, how would we have found it? We would have asked ourselves what will be the perpendicular distance, okay, this distance between the two axes, that is the distance here. We know this is centroid of the axis, we know this is the end, this is the centroid of the rectangle. We know this is the end of the rectangle. So if this is the centroid of the rectangle, we know that if it has height h, then this distance between these two is h over 2. So that means by our parallel axis theorem, we expect that ix should be equal to ix bar plus a, that's the area of the rectangle, which is bh, multiplied by d squared, which is the perpendicular distance between the two axes, which is h over 2 all squared. So will this give us that result up there? So let's check it out. This is bh cube over 12 plus bh multiplied by this is h squared over 2 squared, which is 4. So this is equal to bh cube. So this is bh cube over 12. This is also plus bh cube over 4. So we can add this up and multiply this by 3 so that this becomes 12. This is 3bh cube over 12. So 3 plus 1, that is 4bh cube over 12. So 4 here 1, 4 here 3. So obviously this is going to give us ix, moment of inertia about the x-axis, to be equal to BH cube over 3. Is that the same as what we had before when we solved from the first principle? Yes, BH cube over 3. You can verify the same thing for IY. So this they don't have to be sorry, they don't have to be horizontal axis. So please don't get carried away by that. I've used horizontal axis in the illustration. It applies to any axis, whether it is vertical, whether it's horizontal, or it's at some angle. Once the two axes are parallel and you know the moment of inertia of the one that is through the centroid of the area, please. It is the one, this thing here has to be the one that is through the centroid of the area, please. It cannot be used to relate x1 and x2 because none of them is through the centroid of the area. The one of them has to be through the centroid of the area. So it can be that you have ix2 and you want to find ix bar. That is fine. You just change, you just make ix2, where is my ix2? You can just make ix bar the subject. That means to be ix2 minus ad2 squared. That is fine. But for two axes and none of them is through the centroid of the area, you cannot use this. This one here that you're adding to ad2 square has to be through the centroid of the area. Please, this is the most important thing about this. I'm tempted to say this is the only important thing about the parallel axis theorem. If you don't know that it only applies to an axis through the centroid of the area, then you don't know parallel axis theorem at all. So please and please, you can check for yourselves what happens. We already know IY bar from what we've done. You can also play around with it to see that when you use the parallel axis theorem here to obtain IY, it will give you the same result as what we had there when we solved from the first principle. So that is that about the parallel axis theorem. So these are the fundamental things about centroid of area. Please and please pay attention to this. When we're taking this centroid of area, we can see that it is second moment of area. We know that area is in meter squared, I mean length squared in dimension, and second moment too is length squared in dimension. That means our result should always be a length to power 4 in dimension. So you should expect a length to power 4 dimension in your result. If you get a result that is not length to power 4 in dimension, that means there is something wrong with the process you have gone through or the formulas you have used. Okay, that is one. Another thing is that moment of inertia is always positive. It is always positive because it involves squares in both cases. Okay, so it involves squares, square of length or square of whatever dimension you're taking. Area could be negative, but even if you're going to subtract or use a negative area, we'll see how that works when we talk about composite areas in a different lesson. You will still get a moment of inertia that is positive. It is always positive. Okay, so please have that in mind as you walk through all of this and ensure that you do this by yourself. Look at this rectangle and see how it works. So we'll proceed from here in the next lesson to consider the first principal approach to some other shape, and then we look at when we have composite areas, how we get the moment of inertia for them. Thank you for watching.